All right, so we're back here continuing to talk about water distribution. And in this video, we're going to go through an example where we look at how to calculate the flow rate in a pipeline uh, when there's a pump that is being used to move the water to add energy. Okay, and so in this example, we want to look at what happens if we have two pumps. Okay, so I previously talked about the theory of multiple pumps, and the main thing to remember when you have more than one pump and you're doing an analysis in a pipeline is that you need to come up with a combined pump curve for the multiple pumps. Okay, and so if you have two pumps that are connected in series, that means the flow rate through each of the pumps will be the same. And so at each flow rate, you need to add together the head from each of the two pumps to figure out the combined pump curve. If the two pumps are connected in parallel, then they will each be pumping against the same head. That means that you have to add together the flow rates. So they'll each add flow rate at that same head, and you have to add the flows together. Okay, and so in this example, I want to look at how the operating conditions will change if you have one pump versus two pumps connected in series. And so we have an example where we have a pump station that's going to deliver water through this 40 centimeter diameter pipeline. And it's 1,000 meters long, and it's commercial steel, and there's a storage tank that's 25 meters higher that it's going to put the water in, like a water tower. And then we have this pump curve characteristics here. Okay, so I'll just start by drawing a little diagram. Okay, and so we have a tank here, and then we have another one over here. And so we're going from this tank to that tank, and the height difference between the two is, we'll call it delta Z, is 25 meters. Okay, 25 meters of height difference. And then we're going to look at one pump versus, I'll just go ahead and draw the second one there in series. Okay, and so these two are both going to be pumping the same amount of flow, but they're each going to add head. Okay, and going from one spot to the next. Okay, and so we have our flow here, Q, that we're trying to figure out for one pump or two pumps. And then we have our pump characteristic curves over here that tell us how much head we get at different flow rates. And then we also have to think about the losses here. Okay, and so we have, in this example, the diameter of the pipeline is 40 centimeters, so I'm going to go ahead and do a little unit conversion for that. The length of the pipeline is 1,000 meters. Okay, that's how long this is. So there's going to be head losses from friction there. So we need enough energy to overcome the 25 meters of potential energy gain that we're putting in, and then plus the head losses to overcome the head losses in the pipeline. So we got the diameter and length, and then we have our roughness height here. So this is commercial steel, and so for a particular pipe you have to consider the material. It's going to have a different amount of friction loss, and so that's characterized by our KS value here, which is 0.045 millimeters in the table that I found. So you need to go find a table for whatever material you are looking at for to get your KS value. Okay, I think that's all the information we have in the problem statement. We're also going to need to do this. I think we're going to need the acceleration due to gravity. And so here we're working in metric units, so we'll use 9.81 meters per second squared. And then we will also need the kinematic viscosity of water in order to get the Reynolds number to get the friction factor. And so that is about 10 to the minus sixth meters squared per second. This is at 20 degrees Celsius. So this is kind of all the information we have in the problem. And then we have our pump curve here. And then here I'm going to make an H for, I'm going to call it H series. Okay, so this is the amount of head that the pump will add at different flow rates. So as you look at more and more flow, the pump is able to add less and less as the velocity through the pump gets bigger. It's not able to push as hard on that water, so you get less out of it. And so again, so here we're just going to be looking at two in series. You could also do this problem for two in parallel. And again, it's just a matter of coming up with the combined pump curve here. So for two in series, so when they're in series, we add heads at a given flow. So that means at a flow of 0, the first gives us 30, the second gives us 30. Since they're the same pump, this is pretty straightforward to do. So we just get 60 from the two together. At 100, we get 29.5, and then if there's two of them, then it's twice that, so it's 59. Now, if you're looking at two different pumps, then this is a little bit harder to do, and you often have to kind of do it graphically if you just have the curve instead of a table. But for this one, it's pretty straightforward, so we just double all these numbers, and so we'll go 56, 50, 38, and 8. This is what we'll get. Okay, so what we're going to do is we need to plot the pump curve here, given this operating data, and then we also need to plot what we call the system curve. That is the amount of head that is required to push water at different flow rates here, and that intersection point with this curve will tell us where the one pump will operate, and the intersection point with this curve will tell us where the two in series will operate. Okay, so in order to come up with our system curve, so we need system curve to do this, and we'll use an energy balance to figure that out. Okay, so there's two parts to pump curve analysis always. There is the energy you get from the pump that is given to you by the pump manufacturer in the form of the pump curve. Here it's tabulated. Often it might just be a graph that they give you. Okay, and so then this is the energy that is input from the pump. Then we need to know how much energy it takes to move water through here. And to do that one, we have to set up an energy balance. Okay, and so the basic idea is the energy here at point 1 plus what we add from the pump minus the losses along the way should be equal to the energy we have at the end. So energy at 1 plus the energy from the pump minus the head loss should equal the energy at point 2. And we will do this analysis in units of length or in head. So we use head as a way to talk about energy in pipes. So when we do that, and then we have to think about the different components of the head, and so the components of the mechanical energy here, which is all we're interested in this problem because we're not dealing with like heat transfer or engines. So we have the energy at point 1 here, so we will use point 1 as the surface of this reservoir and point 2 is the surface of that reservoir. And here you have the potential energy from gravity, you got the pressure energy, and you've got the kinetic energy. And so since we're choosing the top of these points, they're both exposed to the atmosphere, and that means the pressure will be the same, and the velocity is going to be negligible at the surface, and so that means we can neglect the velocity. And so again, we can draw these points anywhere we want, but we just need to be smart about it. And so this water molecule can go through to that point. You can pick any points you want, but you want to make sure you pick the ones that make it easy. Okay, so to rewrite this, then we can say P1 over gamma, the pressure head, plus V1 squared over 2G plus Z1, and then plus the head added by the pump, which we don't know. We need to find that. We don't know the flow rate, and we don't know the head that's going to be added by the pump. Okay, and so again, this tells us what we would get at different flows. Since we don't know the flow, we don't know this. So we got kind of two equations and two unknowns for these. One equation will be the pump curve, and the other one will be the system curve. And then I'm going to move this head loss term over to the right. Okay, 2, we have P2 over gamma plus V2 squared over 2G plus Z2, and then plus the head losses. And so for the head losses here, we're going to neglect the minor losses, and so we'll just have the friction losses here from the friction loss in the pipeline, and so we use the Darcy-Weisbach equation for that. So it's FL over D V squared over 2G. I want to make it clear that this V here is the velocity inside the pipeline, which is different than V1 and 2 at the surface of the reservoir. So as I said, those points are going to be negligible velocity because at the surface, and then they're both atmospheric pressure, so those are the same. And so then we basically can simplify this to just say the energy that is required by the pump is going to be equal to the delta Z, the height we're lifting the water, plus FL over D V squared over 2G. Okay, and then so this is the system curve. And this consists of the static head, the head to lift the water, plus the dynamic head. Okay. So these are the terms that we use to analyze that. Okay, so to figure out the dynamic head, we need to, that's going to vary at each flow rate, because as the flow changes, the velocity is going to change, and as the velocity changes, the friction factor is going to change. So we'll need to get the friction factor at each velocity we consider, but we also need to consider for that the roughness height for this particular material, which we said is 0.045, and we get the relative roughness, which is our dimensionless number we use in the Moody chart to figure out the friction factor. And so Ks over d is equal to 0.045 divided by the diameter, which is 0.4 meters or 400 millimeters. Okay, 400 millimeters. Okay, and that comes out to be 0.00011. Okay, so at each velocity, so our strategy here is we're going to have to draw the pump curve here out, and then we need to consider each of these different flow rates. At each of those flow rates, we need to get the velocity, okay, which we're going to need here. And then once we have the velocity, we can get the Reynolds number. And then once we have the Reynolds number, we can get the friction factor from this number and the Reynolds number. And then we can plug the whole thing in to get the total head required, HP, at that flow rate. And then we can plot the system curve. All right, so we're going to, for each flow, we need to get V, and then we need to get the Reynolds number, we need to get F, and then get HP that is the required. Then plot the pump curves. Okay, so the pump curve for one pump, and then the pump curve for both of them in series, and this system curve. Plot pump curve and system curve and find intersection, which we call the operating point. Okay. Okay, so that's what we're going to do. And so I've got here on the next page a little table here where we can plot this out, and I'm going to, up here, I'm going to tabulate all the numbers I need, and then down here we'll do the plot. Okay, so we have Q, and that is in liters per second, and that is given on the last page here. And so we have, I'm going to leave like lots of space, so we have 6 numbers, so I'll leave lots of space to try to make them line up here. 0, 100, 200, 300, 400, and 500. Okay, and then we need to get, so for this, then we'll need to get, so this is in liters per second, and I'm going to need the velocity. So I'm going to set it up the way you would like in a spreadsheet. I'm going to go ahead and write it all out by hand, but this is the kind of thing obviously you would do on a computer. It would save you a lot of time and effort if you did it on a computer, and you'd have a lot less chance of making a mistake, but I'm drawing it by hand here. So we'll do Q. I'll go ahead and convert it to meters cubed per second first, because we need to do that to get the velocity, which we'll do in meters per second. And then we'll get the Reynolds number, which is dimensionless, and then we will get the friction factor, and then we will get H system, the system curve, and then we will get H for, we'll also retabulate here the numbers from the last page. So H from, I'll call it H single, and then H series, okay, from the last page. Okay, so we can go ahead and write these in because we already know them. 30, 29.5, 28, 25, 19, and 4. And then for the two in series, 60, 59, 56, 50, 38, and 8. Okay, so these are our pump curves for the two cases, and then we need to fill this out. So, okay, going to meters cubed per second, 0 is still 0. This becomes 0.1, 0.2, 0.3, 0.4, and then 0.5. To get the velocity here, we're going to do, this is, so it's a circular pipe, so it's Q over A, and the area here is pi d squared over 4. So we might want to do that number. We could compute that, I guess, so that we didn't have to write it out as much, but it's Q equals VA, so therefore V is equal to Q over pi over 4 d squared. Okay, to get these numbers. And so at like 0.1, for example, we would just divide 0.1 by pi over 4 times 0.4 squared, and so that gave me a number of 0.8 meters per second. Okay, and 0 is obviously still going to be 0. Next will be 1.59, and then 2.39, and 3.18, and 3.98. Okay, these will be the velocities at each of those flows. And then to get the Reynolds number here, we're going to do dV over nu. Okay, so the diameter is 0.4, and then we have the velocity in this column, and then divided by nu, which was 10 to the minus 6th. So I'm not going to like write out that calculation, but okay, for 0 it's 0, V is 0. So for the next ones, we get 3.2 E5, 3.2 times 10 to the 5th, okay, and then 6.4, E5, 9.6, E5, 1.36, and 1.6, E6. Okay, so these are the Reynolds numbers for each of those velocities. Again, dV. So these numbers are changing, but d and nu are the same each time. Then to get the friction factor, you can get this from the Moody chart. If you're doing it with the computer, you might want to use the Swamy-Jain equation. And I've done other videos where you look at how you can use the Swamy-Jain equation, let's say, or Moody, to do that. And so you need both the relative roughness from the last page, 0.00011, and then you need the Reynolds number here, and then the Swamy-Jain equation takes those two inputs and you can use it to compute F. Okay, or you can do it again by looking up the number in the Moody chart. So the y-axis will be the Ks over d value, the relative roughness, and then the x-axis is the Reynolds number, and you read off the friction factor on the left side. Okay, and again, I've made other videos talking about how to do that in Excel or whatever. We have the pipeline. Okay, so when I went and did that, if you're not familiar, I'd suggest you go look elsewhere. Make sure you know how to do that. So I got here, let's see. Okay, there's no real friction factor, is kind of undefined for a zero flow rate. And then we get 0.015 and then 0.014. And you can see that these stop changing after a bit, because if you look at the Moody chart, the Reynolds number becomes unimportant. As you start going to higher and higher Reynolds numbers, then these values all kind of become the same, but we're almost there on this one. 0.013, sorry, this is 0.0134, and then 0.0132 in the last one. Okay, so this is the friction factor, and then this is FL over D, V squared over 2G. So we have V over here in this column, we have F right here, and then L is 1,000, and D is 0.4, and then G is 9.81 meters per second squared. So you can plug all that in. Again, this is easy enough to do with a spreadsheet if you set that up, which is how I would suggest you do a problem like this if you were ever doing it for an actual design. Okay, so the first one, there's no velocity, so there's no head loss. But then we need to add in our delta Z. And so our delta Z, so our friction loss is 0, but we need to add in the static head, which was 25 meters. Okay, sorry, so this is 25, and then 26.2 here for this friction factor and this velocity, plugging that in there. Okay, and then 29.5, 34.9, and 42.4, and then 51.7. All right, so all that work here to fill out the table. Now we have each of these flows, and we have the energy required to move the water here. This is the energy we would get from a pump here, and this is the energy we would get if we use 2 of these pumps in series there. So we need to plot these 3 graphs on the same chart and find the intersection point. Okay, and generally you have to do this graphically. I would still suggest you do it with Excel if you're doing this, but you could also write a program, I guess, to try to find the intersection. But I'm just going to plot it here the old-fashioned way. Okay, and so we'll have H in meters on this axis, and then we'll have Q in liters per second here. And I'm going to use every line as a 50 liter, and so this will be 100, 200, 300, 400, and 500. These are all the ones we have. And then the head here is going to be, I'm going to go up by 5 on each line. So this will be 10, 20, 30, 40, 50, and 60 for those different lines. And so we'll start by plotting our system curve, I guess. So it's 25 at 0. And then it's 26.2, so that's just a little bit above here, 1/5 of the way between. And then we'll do 29.5, which is just basically at 30 right there. And then 34.9, which is about at 35 right there. And then 42.4, so that's about halfway between the 40 and the 45 line there. And then 51.7, so just above the 50 line there. So this is our system curve that we then need to kind of connect the dots on smoothly, ideally. Okay, and this is our system curve. That is the energy required to move water in this system. And then we need to plot our pump curves. So we have, let's do the one pump first. So it's got what we call a shutoff head here at 30. That's the max head you could get out of it if there was no flow, which is doesn't really make sense if there's no flow. But that's the most you could ever possibly get out. Then we go down to 29.5, which is, basically just barely under that line. 28, so about right there. And you can already kind of see where the intersection is going to be. 25 here, and then 19, which is just below the 20 there, and then 4, which is about right there. Okay, so this is one pump. Okay, one pump here, curve. And so our operating point there is going to be about a flow rate of, it looks like about 100, and I have it at 170 or 180. So one pump will have Q is equal to, I put it as 170. that's what I had worked it out as, and it looks pretty close. And then the head that we get there is about 28 or 29. Okay, and so that's going to be, we'll go with 29 meters. And then for now we need to find the intersection of the system curve and then the combined pump curve for 2. And so for 2 in series, we start here at 60, and then we go down to 59 there, and then 56, 50, and 38. Okay, and that's where the intersection is going to be, and then all the way down to 8 here. Okay, so our combined pump curve here for darn it, that's why you don't do this in pen. That's the wrong point. It needs to hit that point there and then drop off. Okay, so our operating point is going to then be right there, a little bit below 400 it looks like. So I did for series pumps, I get that Q is equal to about 380 liters per second, and then H for the, I called it H both, is equal to 41 meters. And so if you want to think about the like energy cost from this one, that means each pump is going to give you half of that, because there's 2 of them that combine to give you 40. And so the head each, so H for 1, if they're in series, is going to be half of that, 20.5 meters. Okay, so if you wanted to know like the power cost here to go from one, so if you do 1 pump you get 170 liters. If you do 2 you get more than twice the flow you can see here to 380. The power cost, then you would need to do the 380 times 20.5 times gamma, that's the power divided by the efficiency, for 1 pump, and then you double it because there's 2 of them, and then you can compare that with the power cost for the 1 pump if you were going to do that. I didn't actually do that calculation, but just as a bit of an aside there. So anyway, this shows you how you can use a pump curve and how you can look at more than 1 pump in series if you're trying to compute the flow.